I'm Bapi Golder and I'm from Australia. And I'm going to introduce today Robert King, and he's going to talk to us about making a scalable course search engine with Python. Robert is a serial tech entrepreneur and he makes cutting-edge apps with Python. Some of his Python application he worked on reaches towards 1,000 queries per second. Robert has won many national awards on programming, amongst which is fastest qualifier for Facebook Hacker Cup in 2013, and he's amongst the problem setter for PyCon Code Word 2013. He co-founded Perplexico.com code tutorial. Is that the way to say it? Robert, did I say it right? And he's also the co-founder for studentcoursereview.com, and I'm sure we'll find out more about it with Robert. So please welcome Robert King.
All right, thanks for that introduction. So firstly, I'd like to thank all the sponsors and the organizers. You have to thank them or they don't let you talk. But seriously though, it's been a great conference. Great to see so many passionate people about Python here and people venturing from overseas to New Zealand for the conference. So I'll be talking about Student Course Review, which is an app me and a few friends made last year with Python on the Google Cloud. So I won't be showing you how to get your data into the cloud, but this is how you do it. Hopefully I'm going to show you that cloud computing doesn't have to be rocket science, and it's more like riding a bike as long as you don't try to build your own cloud and infrastructure. So I was looking through the code last weekend, which I wrote about a year ago, and this is the first slide that came to mind, but hopefully we should be okay. So where did it start? So I started building websites when I was a little kid. There was a game I was passionate about, and as kids we had way too much time on our hands, and this is a couple of years before before WordPress came out, so there's some blogging software created in Wellington, I think, called bblog, and to use that, made the site, and a bunch of people started contributing, started making some money off ads, and it was pretty cool. Went on to build a bunch of like leagues and tournaments and things for this game and a bunch of websites, but that was all PHP. When I got to university, I got to use Python properly, and it was a relief having some syntax that was quite nice and being able to build things other than web applications. So the first proper project was building a ray tracer with Python. So I appreciated that it was good for scientific computing and programming contests and very productive. And since uni, worked at a data mining company with Python, built a bunch of web applications, answered some questions on Stack Overflow, which really helped me get familiar with the Python syntax and things like that. Built Student Course Review, which we're talking about today, and for almost the last year I've been working at Hapara, who are silver sponsors today and flew me down to this conference, so I thought I'd better give them a shout out. So this is the dashboard I've been working on recently at Hapara, and it's currently in closed beta. But what you're seeing here is a teacher's dashboard for one of their classrooms. And so basically Hapara is looking for 5 new developers. We're growing quickly. We've got 6 developers based in Auckland currently. And this product is I think about $6 a year per student, and recently expanded to about 40 countries. So it's doing pretty well, so it's a good gig to get onto. And so I built this front end with AngularJS. It's completely client-side and talks to the server only using APIs using cross-origin resource sharing, but the backend's fully Python with Google Cloud endpoints. Let's close that. Okay, so building all these apps and building things from scratch, the first 10 times didn't get it right at all. I mean, the first website I made with PHP was probably a few thousand lines of code inside a for loop, inside a while loop, inside index.php with no functions or classes. But after building a few things, you get good at refactoring and good at thinking about design principles. So a lot of people just jump into legacy code and don't build things from scratch. So I recommend doing some of your own projects. But even if you've built a lot of things, this is usually what ends up happening. Okay, so student course review is my friend came to me about a year ago with a prototype for it. He's not a programmer, he's more into biology and things like that, but he wanted to build the site. So I said I'd help him out. We wrangled a few friends together and hired out an office for a week for like $200, and I think it was a free coffee machine, so we probably got about $200 of coffee. And before we started building the site, we called up Monster Energy, and they said they're going to send a truck of energy drinks to Auckland University to launch the site. So we knew we had a hard 2-week deadline. So I'll show you the site, if I can go to it. So basically there's a few ways to navigate. You can click on your country and select your university and drill down through the faculties and departments down to your courses, or you can search for a course. So if I go law, which is probably the slowest query we have because it's got more than 1,000 results, so that took a little bit too long. If I search for it again, it's pretty much instant because it's now in Memcache. But basically you can go through the universities. It counts how many results there are for each university. Go BioSci, it's popular at Auckland University. So anything with a yellow stars means it's been reviewed. So you can click on one of those. You can read some of the reviews and write reviews, upvote reviews. And then you might want to see some stage 2 papers. You use the breadcrumb. And most of these pages is just a single key lookup to get the data that you need. So that's the site. And then if anyone has any feedback, that'd be appreciated. There's a feedback button here, which you just type in your feedback there. So is it scalable? Well, at the moment, if you search for law, that's pulling about 1,000 database entities, which would be a little bit expensive at scale, but App Engine's going to replicate those hotspots in the data store, so it can handle it. It's just going to not be that cheap. If I open up this video, so a lot of the time the website's not getting that much traffic, and but when people are choosing courses or just after exams, then it gets quite a bit of traffic, especially when someone writes a funny review, might get posted on a big group on Facebook. So we've had times where it got posted on a Facebook community that had about 100,000 followers, and then people from that group posted it on other communities, and all of a sudden you got like 1,000 people hitting the site searching at the same time for maybe like 10 or 20 minutes, and that might cost you kind of 20 cents or something like that, and then so it doesn't cost too much, and then the rest of the time it's pretty much free. So being on a cloud with auto scaling means those expenses are kind of taken care of. Okay, let's go back to the presentation. So okay, so I'll jump into some code and show you how the search is currently implemented. First I'll show you some of the basics just to show you this stuff's not too hard. So if I open up routes, when a request comes into one of your instances, which is a kind of long, complicated process, but eventually your request will get to this piece of code and get matched against some routes. So for example, if someone submits some feedback, it's going to go to this feedback handler. That feedback handler takes that request and works out the correct response to send back. So this was written by my friend. She'd never done any Python before, hadn't done much programming before, But when she came into the office and was able to just start contributing straight away, and that's one of the good things about Python. So if it's a GET request, it just gives them the feedback template. If it's a POST request, then it creates a new feedback model. So if I show you that, Command B to jump to that. The main property is a text property, which is the content of what feedback they wrote. We've got like a date time property, which is automatically created at the date that the entity was saved to the data store. And you see this is an NDB model, which is, so NDB is your way of interfacing to the App Engine data store, which was created by Guido. He created NDB. And I think that might have given him inspiration to make async IO in Python 3.4. But so this feedback, basically you use classes, it's all kind of abstracted, and they're very easy to use, but under the hood it's kind of persisting to data store, which is going through Megastore to Google Big Tables. And this is rolled out into a row in Google Big Tables, which is like a massive table ordered by key. So if we jump back, we're just grabbing the feedback type and the feedback content from the request. And then we're just going feedback.put. So it's all pretty straightforward. So you're in the cloud, but you don't have to really worry about it. Like, you don't have to really know much about the cloud to start using it. If I jump back to routes and look at search, what basically happens is it gets the search term, which is what they're searching for. And another thing you can do when searching is you can specify filters. So you can filter, I only want to search these universities. And so it looks the search term up in memcache. So it gets the memcache key. If it's not a memcache, if it is a memcache, it just writes the page to the response. Otherwise, it's going to call this getCourses function. Now, this takes the search term, the university keys, and a default limit of about 1,000. So this is the way we started off with search was just quick, because we needed to get things done quickly. And that's the beauty of Python, is you build things quickly, then you analyze things later and figure out how to make them better. So here we get the term, and we want, say they search for bio, we want to find everything that starts with bio, like bio 101, bio 102. So we just have the term, and then we add a Z to it, and we get all the courses that have names between bio and bio Z. And it seemed to work pretty well. So here we've got our course model. It's a little bit more complicated than the feedback model, but it's still pretty simple. Just has a name, country, university, faculty, department, stage, and so on. And also, if they provided some UniKey filters, then we want to filter that query to only get courses that have a university that are in those university filters. So this is, once we actually run that query, this is the expensive part. And queries on Bigtable are always kind of proportional to the size of the results. So if you're returning a lot of entities, then it may be slow, but generally it's pretty quick because people type in the exact course code. So the great thing about Python, so Python may be a little bit slow, but most of the time is spent doing those data store fetches, and all those APIs are implemented in like C++ or Java or something like that. So if you use something else instead of Python and make it maybe 50 times faster, since Python's only spending a small percentage of the time, you're only speeding up a small percentage by switching away from Python. So you're better off analyzing your data and improving your queries. So since we record all of the search lookups, we can plot popular search terms. And you can see 50% of these, a small number of search terms take up 50%. So we could actually store those results for those in memory rather than going to the data store, and that would cut out half our costs. And being productive with Python means we've got time to do those kinds of things. So what we can do is create a try tree data structure where as you traverse, you can find course codes. So if I go to the right and go L, then A, then W, then that's law, and so on. And at the bottom of each node, I can have instructions of data store lookups based on that result. And I can, from each node, I know how many possible course codes there are that match beneath those nodes as the sum of the nodes beneath that node. So that's something that we're implementing at the moment. If we need to expand to more countries and once there's more results in the system. So scaling can be difficult. Generally, you start off with a single server, make it a bit bigger, make it a bit bigger. Then you start hitting a problem when you've already got the fastest computer and you need a load balancer, a couple of computers, and then all of a sudden you can't use state anymore, so you've got to be stateless. And then you end up maxing out the hard drive speed for certain bits of data, so you need data replication. And if you've got data replication and you update part of the data and someone else reads from a replicated piece of that data at the same time, since you can't update all the places where that piece of data is replicated at the same time, you're going to get eventual consistency, which means your queries won't return the same results depending on which replicas your queries are going to. Luckily, also another thing about this is failure. If any part of this fails, you need to recover from that. So luckily, you don't have to do this stuff yourself. So there's a whole lot of offerings. I'd probably also add Heroku and OpenShift to the mix and a few others. So we went with App Engine just because it's pretty easy for beginners to use. It's basically cloud development in a box. So how does it work? So basically a request comes in from a mobile app or the browser, goes to your internet service provider, and it's going to hit a Google front end. And that's kind of a way into Google's global serving infrastructure. So I guess it does like DOS protection and things like that. The killer feature is the edge cache. And since Google's got data centers everywhere, so for us it'd probably be like Singapore or Sydney, or I'm not too sure where, but a lot of your content can come from that edge cache. And anything from the edge cache is free. You don't pay for that. So say you've got a home page of graphs and stuff on it that are expensive to generate, you might choose to cache that for 10 seconds. And the majority of people will be getting it from the edge cache. So so the way you set up caching is you add some like headers to your response, and it knows how to cache it. If it doesn't find what it needs in edge cache, then there's a big fat pipe connecting you to the next data center, because they've got their global network. So it's quick. You don't have to travel through the internet to the nearest data center that's got your app serving. And actually, when you write to the data store, your write actually goes to multiple data centers. And so you actually need at least 2 data centers to go down before your app goes down, or maybe 3. So I think it writes to at least 3 data centers. And if the majority accept that write, then your write succeeds. So when your request comes through this fiber to the second data center, it will be queued up with a whole lot of other requests. And there'll be a whole lot of instances serving those requests, and it's going to predict how long is it going to take for your request to get served by those instances. So based on how many instances are running and what kinds of requests are queued up, it's going to decide if it'll be faster to wait or if it's faster to start up a new instance. So if your app can load up really quickly, then, so each instance is basically a mini container within a VM, and there might be like 100 containers running within a VM. So if your app's lightweight and can start up quickly, then it's just going to be able to scale really easily, because it can just launch new instances straight away. So like being able to start up your instance in less than a second is pretty good, which is a little bit unfortunate for Django, because that is a little bit more heavyweight. So I tend to go for lighter frameworks, and actually now I pretty much use cloud endpoints, and I don't serve dynamic HTML as much anymore. I just have static clients. So yeah, this is kind of what it looks like. You've got your front ends, and then you've got your App Engine front ends. And then there's a whole bunch of services like the data store, which I mentioned. There's Memcache, which is a key value store, which is really quick, and that's a lot cheaper than data store. And there's a bunch of other services. But I put a lame joke in here, just because, so we can move on to talking about some other stuff. But if anyone hasn't watched Harry Potter, he could talk to Pythons. All right, so with data replication, it's a little bit more expensive doing write. So you're concentrated on making apps that read a lot but write less often. And that's kind of a problem. Let's say you can only update one of those rows in the table about 5 times a second. What if you want to count page views and you're getting millions of views a second? Then you can have something like a sharded counter. Like, let's think of like the election night. If we had to count everyone's vote with one person, it would take a long time. But since we have lots of polling booths, then we can just add up the votes at each polling booth and count all the votes really quickly. So that's kind of how a sharded counter works. So each of these lower nodes are going to pass their counts upwards. So 3 plus 2 is 6. And then 6 plus 14 plus 7 equals 27, and so on. So I was going to do a live demo. We might save it to after questions if we've got time, where I was going to see how many people are in the room. So the guy in the middle could kind of divide the audience into 4 quadrants and assign people in the middle of those quadrants to recursively count how many people are in their quadrants, and then see how quickly we could count all the people in the room. And each person would add up the numbers from the people below, the 4 people below them. So when you're kind of doing cloud stuff, you're using like task queues, and you're kind of thinking of all these things kind of like factory conveyor belt systems and like all these moving pieces. So I've got a little bit of an implementation of a sharded counter here, which I might go over a bit later, but it's pretty short. I'll just go over it. So we have a simple shard. Sorry, I'm going to have to do this a little bit quickly, but we have 20 shards, which means each shard has a count, and so to read the value, to get the count, we just loop through all of the shards, and we add it to the total and return that. And when we want to update the total, we randomly choose one of those shards. We increase that inside of a transaction, which means no one else can increase the number at the same time as us. And we save that. And I was going to show you a Java example, but I couldn't fit it in my presentation because it was a bit long. But that's one thing. Also, another thing about the instances starting up quickly in like about a second for those containers. Java takes a bit longer to start up. So even though Java is quite fast, it can actually use a bit more memory and start up a bit slower, so it may not scale quite as well at times. And all of the examples they have, because it's all infrastructure, it's kind of language agnostic, but then it's implemented in many languages, which is kind of safe because you're kind of, if all the other languages are doing similar things to you, then it's a little bit safer. But you always have like the Python example and the Java example. And the Python example is always like really easy to read and a lot shorter. So I've got a little bit of time, so I'll quickly go to a live demo. So firstly, here's like a simple counter that I created where it had a, yeah, I've got 1 minute left. So I'll go for like 2 more minutes. So this one is a simple view count. So it writes out the count. But if 2 people visit this page at the same time, they're both going to grab the count at the same time. So let's say it's 5, and then they both increase it to 6, and they both save it to the data store. Then, you know, it should have really gone to 7 instead of to 6. So that's one problem with not updating these numbers in a transaction. So if I open this counter 3, this is like a cheap counter which doesn't quite count everything, but it's pretty accurate. And what we do is we store part of the count in the data store. It's expensive writing to the data store, so if we instead of writing to the data store every time, we only write to the data store every few seconds, then what's going to happen is it's going to be a lot cheaper. Like say we're counting something 1,000 times a second, then it's going to be 1,000 times cheaper if we only write once every second. So to get the count, part of the count is stored in data stores, part of the count is stored in memcache. The problem with memcache is it can get wiped, and memcache isn't that reliable. So, so what we do is, to get the count, we have the persisted count and we have the memcache count, and we return the sum of both of them. To increment the count, we use this memcache.increment method, which can run maybe 10,000 times a second or something like that. It's very cheap. We can get an interval number from basically using the number of seconds since epoch and dividing that by 5, then we'll get 5-second intervals. We create a task with the interval number and the task name, and we defer that task to run kind of 5 seconds in the future, and that task is only allowed to be created once. And so this task flushes the counter, and so this flush counter method basically grabs the current value in memcache, it decrements memcache by that amount, and then it saves, it increases the persisted count by that much, and then saves. So there's a few problems, like if this fails, then you're going to lose that amount from memcache. There are ways to set up retries, and also, what else? You're kind of assuming that all the instances have accurate time to within like a few seconds, which they should be kind of accurate to within 100 milliseconds or something, using like network time protocol or whatever it's called, but it's a little bit risky. And I have one test for that. Oh, I've got 2 tests for that. Test counter 3, which we get the count and we get 0, increment the count, get 1, and so on. Then we check that memcache has the right amount, and then we can flush the counter and make sure that memcache and data store have the right values. And the way this works, this in-memory test works, is we've got a base test handler which sets up testbed, which mocks out memcache and the data store and all of those services, and puts stubs in memory equivalents. So that, and then to test that in production, we've got this counter load tester, which grabs a pool and runs a whole lot of processes. So if I run that, but I'm going to set it a little bit higher, 5 processes. So I'll run that and then I'll take some questions. And you're normally meant to kind of slowly add processes, because otherwise to kind of warm up the site first. So here it's kind of, I accidentally ran that with coverage, but that's all right. So we got up to 3.6 counts a second. Maybe 10. I don't know if I'll get rejected or not, because they might think I'm trying to like DOS the site, but normally you're meant to kind of slowly warm up your load tests. So we got up to 4 a second, and I got it up to like 15 a second, and I didn't really bother going that high, but hopefully it should go to kind of 10,000 a second or something like that. So yeah, any questions?